Hello everybody, I welcome you all to my second lecture on the three-phase circuits. In the previous lecture, I have discussed the analysis of three-phase balanced circuits and some tutorials on three-phase balanced circuits. In today's lecture, I am going to discuss some more tutorials on three-phase balanced circuits and then move forward to the analysis as well as tutorials on three-phase unbalanced circuits. Given that in a three-phase, three-wire system of star-connected load, it contains 50 ohm resistor, 5 microfarad capacitor and 0.56 inductor in series in each phase. Considering positive phase sequence with a voltage VAN 390 at an angle 30 degrees VRMS and omega as 500 radians per second, it asks us to find VAB, VBC and VCA. So as I told you in the analysis of three-phase balanced circuits, there are two ways by which we can designate the three-phase quantities, either by following the phase sequence RYB or ABC. So in this sum, he has followed the phase sequence ABC. So given R is 50 ohm, C is 5 microfarad and L is 0.56 Henry. Since given that all are in series and omega is also given as 500 radians per second, we know the Xc, that is capacitive reactance, can be written as 1 by omega C and inductive reactance XL can be written as omega into L. From that, the total impedance in each phase will be R plus JXL minus XC. You know the values of XL, XC as well as R, which will give me the impedance value to be 550 minus J 120 ohms. So the magnitude of the impedance will be nothing but root of 50 square plus 120 square, which is nothing but 130 ohms. So after finding Z phase, let's calculate the phase voltage. Already VAN phase voltage is given as 390 at an angle 30 degrees. Since in a balanced three-phase circuits, all phase voltages are equally displaced by 120 degrees. So therefore VAN, since it has the angle of 30 degrees, by minus 120 degrees it will lag, that is VBN will have minus 90 degrees. Similarly VCN will be 120 degrees displaced from VBN, so we will get minus 210 degrees. The magnitude will be same since it is balanced three-phase circuit. So the line voltages, since this is a star connected system, the magnitude of line voltage is root 3 times the magnitude of phase voltage, and every line voltage will lead the respective phase voltage by 30 degrees. So on substituting the values in the formula, we'll get the expressions for VAB, VBC as well as VCA. So the ninth tutorial, balanced three-phase star connected system with an effective voltage 106.1 volts and load impedance of 5 at an angle minus 30 ohms. It asks us to calculate currents, that is both line currents as well as phase currents. Assuming that this is RYB phase sequence, line voltages as the magnitude is given as 106.1 volts. You know that in a three-phase balanced system, every line voltage will be equally displaced by 120 degrees. Since this is a star connected system, the magnitude of phase voltage will be 1 by root 3 times the magnitude of line voltage, and every phase voltage will lag by 30 degrees with respect to line voltage. So Using that, we'll find the values of phase voltages VRN, VYN and VBN respectively. After finding phase voltages, phase current is nothing but phase voltage by phase impedance. Just now we have calculated the phase voltages and we know the phase impedance to be 5 at an angle minus 30. So taking the ratio will give me the values of phase currents IRN, IYN and IBN respectively. Since this is a star connected system, we know the magnitude of line currents is equal to the magnitude of phase currents. So IR will be equal to IRN, IY will be equal to IYN and IB will be equal to IBN. The last tutorial, 10th tutorial in three-phase balance systems, the RMS value of phase voltages are given as VRY, VYB and VBR respectively. Since this is a delta connected load of impedance 10 at an angle 30 degrees, it asks us to find line currents as well as phase currents. Assuming it is RYB, Z phase is given as 10 at an angle 30. Phase voltages are given VRY, VYB and VBR. Since this is a delta connected system, we know that the magnitude of line voltages is equal to the magnitude of phase voltages. Okay. So phase currents will be nothing but phase voltage by phase impedance. So by that I'll get the values for IRY, IYB and IBR. So after finding the respective phase currents in delta connected system, the magnitude of line current is equal to root 3 times the magnitude of phase current. And every line current lags the respective phase current by 30 degrees, by which you'll get the values for line currents IR, IY and IB. So this is the end of my tutorial session on three-phase balance circuits. So moving forward now to the analysis of three-phase unbalanced circuits. This issue of unbalance in the three-phase circuits in the entire power system is very common nowadays, and this unbalance in the system is due to either unbalance in source or at the load. The issue of unbalance creates additional power losses, and unbalanced voltages or unbalanced loads will ultimately lead to the formation of unbalanced system. Thereby, the neutral current will no longer be zero. The unbalance in the system will also occur if there is any change in impedance in either of the phases. The magnitude of currents as well as the magnitude of voltages will no longer remain equal in unbalanced circuits. Also, since each phases are unequally displaced in unbalanced loads, this complex problem is very difficult to handle. Hence, in order to make our analysis of unbalanced circuits easy, it is assumed that the voltage sources are in balanced condition. So like the three-phase balance system, even the three-phase unbalanced system are of two types, that is three-phase 3-wire as well as three-phase 4-wire. But unlike the three-phase balance system, here the neutral current is not zero. The neutral current is nothing but minus of the sum of all the line currents IR, IY and IB. So the types of unbalanced loads are of three types. It is unbalanced delta connected load, unbalanced three-phase 3-wire star connected load and unbalanced 4-wire star connected load. Since both the sources as well as the loads can be connected either in star or delta, so there are four possible ways to connect a three-phase system: star-star connection, star-delta connection, delta-delta, and delta-star connection. So these are the circuit representation of the various star-star connection, star-delta connection, delta-delta connection, and delta star connection. So in all the four connections, you can observe that the source is assumed to be balanced. So the total three-phase power in an unbalanced system is the sum of individual powers in each phase. That is, P is equal to PR plus PY plus PB, where PR is VRY IRY into cos of the angle between them. Py is Vyb Iyb into cos of the angle between them, and Pb is Vbr into Ibr into cos of the angle between them. The first tutorial, the three-phase, three-wire 440 volt source is supplying power to an unbalanced delta connected load in which the following impedances are given, and if the phase sequence is RYB, line current and phase currents are to be calculated. So since RYB phase sequence is being followed, the delta connection system, the magnitude of line voltage as well as phase voltage are equal. Therefore, VRY, VYB and VBR magnitudes are 440, equally displaced by 120 degrees from each other. Phase currents, I is equal to V by Z. I know phase voltage, I know phase impedance. So taking the ratio of these two will give me the phase currents IRY, IYB and IBR as well. Line currents, since this is delta connected system, the magnitude of line currents is root 3 times the magnitude of phase currents, and every line current will lag behind 30 degrees from its respective phase currents. So from that, IR, IY and IB line currents can be calculated. The second tutorial, three impedances are connected between neutral and RYB phases. The light voltage is given as 440 and phase sequence is given as RYB. Line currents, neutral current and power consumed, total power drawn by the circuit must be calculated. Assuming the RYB phase sequence, phase impedances are given, converting them into polar form. Line voltage magnitude is given as 440 and each line voltage is displaced by 120 degrees from each other. Since this is a star connected system, the magnitude of phase voltage is 1 by root 3 times the magnitude of line voltage, and every phase voltage lags behind 30 degrees from the respective line voltage. So therefore, by this we calculate the values of phase voltages VRN, VYN as well as VBN. I is equal to V by Z, so correspondingly phase currents IRN, IYN and IBN are calculated, just taking the ratio of phase voltage as well as phase impedances. Since this is star connected system, the magnitude of line currents is equal to the magnitude of phase currents. So IR will be equal to IRN, IY will be equal to IYN, and IB will be equal to IBN. Since the load is unbalanced, after finding the line currents IR, IY, IB, you know the formula neutral current is equal to minus of the sum of all line currents. So on applying the formula, I get the neutral current to be 23.54 at an angle 28.85 amps. The power in each phase can be calculated by calculating the corresponding power in each phase PR, PY, PP, and the sum of all the powers in the respective phase will give the total power consumed, which is 19.8 kilowatts. Third tutorial, a three-phase, three-wire 400 volts is connected to a star-connected load. The impedances are given. It asks us to find equivalent delta connected load, and for that equivalent delta connected load, it asks us to find phase currents, line currents, and total power consumed. Since this is star connected load, the impedances are given Z1, Z2, Z3. Equivalent delta connected load. We know the formula to convert the star connection into delta connection. So on applying the corresponding formula, we'll find the corresponding impedances of delta connected system. So Z delta 1, Z delta 2 correspondingly can be calculated by substituting the star connected impedances in the formula, and similarly Z delta 3 can also be calculated in the similar way. So this will give me the equivalent delta connected load. So after finding the equivalent delta connected load, now assuming that the phase sequence is RYB, since this is delta connection, the magnitude of line voltage and phase voltage are equal. Therefore, the magnitude, since it is given 400 volts, and each will be displaced by 120 degrees each. So the phase currents is the ratio of phase voltage by phase impedance. Therefore, just substituting the corresponding value, find the values of IRY, IYB, and IBR. Line current is delta connected system, so the magnitude of line current is root 3 times the magnitude of phase current, and every line current lags by 30 degrees from its corresponding phase current. So on substitution, you will get the values of IR, IY, and IB. The total power is P is equal to PR plus PY plus VB, since it is unbalanced load. So individually finding the powers and summing up all the three phase powers, you will get the total power consumed to be 64.28 kilowatts. So the next concept is the application of Millman's theorem in the analysis of three-phase unbalanced circuits. Or in other words, this method is also called as neutral shift method. And this from the knowledge of Vn dash, which is called neutral shift voltage, as well as the phase voltages of the source, that is VRN, VYN, and VBN. So from the knowledge of phase voltages of the source and the neutral shift voltage, the corresponding phase voltages of the load can be determined. So we'll see this procedure, how to find the phase voltages of the load from the knowledge of source voltage as well as neutral shift voltage. So next we'll discuss the step-by-step procedure, how to find the neutral shift voltage using the Millman's theorem, and from the knowledge of neutral shift voltage, how we can find the phase voltages of the load. The first step, assume the phase sequence as well as the reference phasor and write the line voltages of the given three-phase source. Since it is a star connected system, the phase voltages will lag behind the respective line voltage by 30 degrees, and the magnitude of phase voltage will be 1 by root 3 times the magnitude of line voltage. Since the impedances of the load are known, we will calculate the load admittances and the neutral shift voltage. The formula for calculating neutral shift voltage is VNN dash is equal to VRN into YR plus VYN plus YY plus VBN into YB divided by YR plus YY plus YB, where VRN, VYN and VBN are phase voltages of the three-phase source and YR, YY and YB are the respective load admittances. Next, phase voltage of the load can be calculated by subtracting this neutral shift voltage from the respective phase voltage of the source. Then we calculate the phase currents by dividing the phase voltage of the load by the phase impedances. Then we estimate the line currents as well as powers in the given three-phase unbalanced loads. So this is the detailed procedure to find neutral shift voltage as well as the corresponding phase voltages, line voltages and power in the analysis of three-phase unbalanced loads. We'll see some tutorials based on the neutral shift voltage using Millman's theorem. Here a three-phase 3-wire 200 volts supply is connected to a star connected load. The impedances in each branch ZR, ZY, ZB are given. Line currents are to be calculated using the Millman's theorem. First, since line voltage is given as 200, assuming that the source is a balanced three-phase, so all respective line voltages will be equally displaced by 120 degrees from each other. Phase voltages, since this is a star connected system, the magnitude of phase voltage will be 1 by root 3 times the magnitude of line voltage, and every phase voltage will lag the respective line voltage by 30 degrees. Thereby we will find the values for VRN, VYN and VBN correspondingly. So after finding the phase voltages of the source VRN, VYN and VBN, next load admittances can be determined by the reciprocal of the respective load impedances ZR, ZY and ZB. Now from the knowledge of phase voltages of the source and load admittances, you will find the neutral shift voltage. The formula VNN dash, on substituting the values of phase voltages of the source as well as load admittances, you will find the value for neutral shift voltage. Now from neutral shift voltage, you will find the load phase voltages by subtracting this neutral shift voltage from phase voltage of the source. So from that I'll get the value for VRN dash, VYN dash and VBN dash. So after finding the phase voltages of the load, phase currents I is equal to V by Z. So correspondingly, the load phase currents IRN dash, IYN dash and IBN dash can be calculated. And from this, the line currents, since this is a star connected system, the magnitude of line currents as well as phase currents are equal. Therefore, IR will be equal to IRN dash, IY will be equal to IYN dash, and IB will be equal to IBN dash. Next, the fifth tutorial. Three impedances are connected in star across a 440 three-phase supply, where the voltage of a neutral point relative to neutral is 200 at angle 150 degrees, and the line currents IY and IB are given values respectively. It has asked us to find the impedances of the load ZR, ZY and ZB. Here, assuming RYB phase sequence, line voltage is given as 440. Therefore, each line voltage will differ equally by 120 degrees. So phase voltage will be nothing but, since this is a star connected system, magnitude is 1 by root 3 times the line voltage, and every phase voltage will lag by 30 degrees from its respective line voltage. Thereby, I can find the values for VRN, VYN and VBN. After finding the phase voltages, the neutral shift voltage is given as 200 at an angle 150 degrees. So from the knowledge of phase voltage and neutral shift voltage, the phase voltage of the load can be calculated by subtracting these two values. Thereby, I will get the value for VRN dash, VYN dash and VBN dash. So after obtaining the phase voltages of the load, the line currents IY and IB are given. So from this, the line voltage IR can be found out. Since this is a three-phase three-wire system, sum of all line currents is equal to 0. So IR can be calculated as minus of IY plus IB. So after that, the load impedances will be nothing but ratio of phase voltage of the load by phase current. Since this is a star connection, the line current is equal to phase currents. So correspondingly, ZR, ZY and ZB can be calculated as shown. The last sixth tutorial, I'll leave that as an exercise for you. Here I have the line voltage should be 400 ohm volts. ZR, ZY and ZB impedances are given, and using the Millman's theorem to find neutral shift voltage, the load phase voltages as well as line currents. I leave the answers for you to cross check. This brings the end of today's lecture on the analysis and tutorial session of three-phase unbalanced circuits. In my next and last lecture on three-phase circuits, I'll discuss the concept of three-phase power measurement using 2 wattmeter method. Thank you.